Let's take a look at another proof of the Pythagorean theorem. This one relies on the property of similar triangles. So let's go ahead and talk about what it is we first want to show. So what do we want to show? Well, generally what we want to show is that if we have a right triangle, let's say some general right triangle, whose sides listed in order of magnitude are A, B, and C, then the following is true about those side lengths. A squared plus B squared is equal to C squared. Okay, so one way that we can do that is we can start with a general right triangle. I'm going to draw it in kind of an interesting position, one you're probably not as used to seeing. Draw it this way. So I made sure that this was the right angle up here, and we'll go ahead and draw it in. So my side here would be A, my side here would be B, my side here would be, let's say, C. Well, one of the ways that surprisingly we might be able to prove this is by dropping what's called an altitude when the triangle is drawn in this fashion. Well, so when the triangle is drawn in this fashion, the altitude, of course, will go through the right angle right there. And what this results in is three sets of similar triangles. There's, of course, the big triangle on the outside, who has angles 1 and 2. And then, of course, there's another right triangle in here, whose one angle is, well, here would be the right angle, of course, because we have an altitude that's perpendicular to its base. The angle 1 would be right here, but since 1 and 2 we know add to 90 in the big triangle, that 1 and 2, this one right here, will have to add to 90 in this sort of medium-sized triangle. And in a similar sense, in this smaller triangle, we have angle 1 up in this corner if angle 2 is down in this corner, because 1 and 2 must add to 90 together with this right angle here. So it might be easier if we drew these triangles all in the same orientation. So in a sense what we have is we have one big triangle in there, and I'll go ahead and draw it up like this below. I'm going to try to get roughly the same proportions, but it might not be just perfect. So that's the big triangle. So the big triangle, of course, if I flip it and move it down, the shortest side again is A, the medium-sized side would be B, and the longest side is C. This would be angle 1 and angle 2 in the right angle. And then there's a medium-sized one that would be sort of, I guess it's kind of this range. I mean, roughly, I'm not perfectly redrawing it, but the idea would be I've sort of rotated this medium-sized triangle down here, and now we get a little bit trickier because, of course, here the hypotenuse is, excuse me, not C, but B. So the hypotenuse is B. We don't know what this length is, but this length is something, you know, that's sort of part of C. Maybe what we'll do is call that length. We'll go ahead and call that length X, and we'll call this little shorter length Y. So we'll call this this long length up here then X. And of course, we introduced a new piece up here too, so we'll probably have to give that a name as well. Well, we can't call it Y because we've always used Y, so let's call it Z. So that would be X here, and then Z would be right here. And then the last piece is this little short triangle, about 6 tall or so. Again, trying to sort of make it about the same proportions as the other two, because we know, of course, it's similar. And this short triangle again has angle 1 up here and angle 2 down here. So this would be A, Y, and Z. So that's kind of what results. We get one similar triangle from there. We get, I guess, this guy is a similar triangle from here. And then the whole thing, of course, similar triangle here. And so one of the things we can do with similar triangles is talk about proportionality. And there's all kinds of nice proportionality that goes on here. So if we take a look at the different proportions that we can make. We can say that b is to a as x is to z and z is to y, for example. So that's one way we could do that. We could also go b is to c. And the large triangle is x is to b. And the middle triangle is z is to a. And the smaller triangle. And the third way we could do that would be, well, we've compared b to a and b to c, so b is kind of out now in this big triangle, so the only thing left is to compare c to a. So c is to a as b is to z, as a is to y. And here's kind of where the proof discovery process really comes into play. I can see that in some of these, if I think of cross multiplication, that I can get a b squared and an a squared out. In particular, if I look at this particular equality, I can see that b is to c as x is to b, but cross products being equal, this thing would imply then that b squared is equal to cx. And a similar game can be played right here, where again we have c is to a as a is to y. So here we would have cross products being equal, a squared is equal to cy. And so we have the two pieces of the ingredients of the algebraic expression we want to prove. But now what we need to show is that those two pieces, when summed, are equal to c squared. So the smart thing to do then would be to simply add these two things together and say, well, what is a squared plus b squared? Well, by substitution, a squared is cy, and b squared is cx. So let's see what happens to that. If I factor out a c out of this expression, I get a y plus an x. And that's where things are kind of interesting and lead us quickly to the conclusion, because you have to ask yourself, well, what is y plus x? If I can show it's equal to c, then I'm done, because then it would be c times c. And indeed, if you go back up to the picture, you can see that c itself is this distance from here to here. And if that's the distance of c, and it's made up of x and y, then x plus y, the distance x and the distance y, is indeed equal to c. So we can replace that with c times c itself, which is equal to c squared, and that proves our proposition that a squared plus b squared is equal to c squared.